Sharing your video, if you're in a place you can do that, that's wonderful. It just makes the user group meeting that much more fun, and for us all to be together. Next meeting will happen May 20th, so it'll be like 5 weeks until the next one. Zoe's going to present her presentation on UI, making really attractive reports that she's worked up and already presented, I know, at least once. So it's going to be great. If you missed it, you can watch replays from this event, this business applications launch event. They talk about a lot of the new features. It really crosses like Dynamics and Power Platform and Power BI. I didn't really hear, as I was listening, like any big new announcements about Power BI. It really was just kind of a sales pitch about, or a case study. But if you're interested in, high level or like applied business case studies, you could check out the videos and content from this event. I thought the presentation that Patagonia did with Dynamics was pretty cool, and they did a good job selling Microsoft's products for them for sure. So our next meetings, just to repeat, May 20th will be our next one. June 17th, we'll have Melissa Coates talk to us. She has a number of presentations to choose from, so I'm still narrowing down which one to go with. And then July 15th. And and let me pull up what the new community page is going to look like. If you're not yet part of the Power BI communities. Now you might recognize this site if you were on our meeting 2 months ago. Zoe actually, because she's a super user on here, walked us through, here's how you use this, community.powerbi.com. Well, in a couple of months, this is actually where our new home for our user group is going to be. I hope a couple of months. I actually just went through the process of, we had to request our group to be set up on this site. I guess they also don't migrate over any content. So we'll have to get people signed up here again. But when we do, the great thing about this is there's way more content on community.powerbi.com than there ever was on our user group. So you can just see tons of articles, tons of posts and Q&A. In fact, wow, here's Zoe commenting on some ideas about data lineage. So I think when the groups, I'm not sure how the groups are going to look exactly, but it's going to be nice that your profile on here will be linked to that, and just be one place for your whole sort of community presence in the Power BI world instead of two places. So that'll be cool. But I'll have more information as we get our group set up. Still just waiting to kind of see what it's going to look like. And I know it's been weird, but a lot of this stuff is happening on the fly. I think Dynamic Communities had sort of an unplanned shutdown is probably the word for it. So that's that. So just to go over a couple of some of the new features in data pipelines, or data flows, I'm sorry, wanted to mention. So for one thing, if you don't have premium, you haven't been able to really appreciate data flows before, but now that premium per user is GA'd, you can take advantage of that. You can do a 60-day trial. And what you do to do that, I'll show you the same thing that I showed Zoe the other day, is you have to click on your little icon up in the corner. And when you click that icon, if you haven't already done it, you will get an option to do a upgrade to it says pro account premium per user trial. I already started mine, but click on your little icon up here at the top and you'll see some options there. So that's one thing. If you haven't had premium before, then you weren't able to see data flows, and you were probably like, what's all this talk about data flows and why do I care, right? So I think I need to go back to where I was. Oh, there we go. Data flows authoring. So yeah, anyway, they're changing some comments and things like that. So anyway, so check out data flows. If you use data flows, you might want to see what's new from this month. And it doesn't look like, it doesn't look like they changed things too fundamentally, some language changes and things like that. Just something to keep an eye on of what's new. The other big announcement, though, I did want to mention, I know this is a little obscure, but it's important. They talk about object level security is now generally available. So what is object level security? That's really talking about being able to put special security at a column level and at a table level inside the model. So for a long time, they've had row level security. So I could say, setting up those roles, I could say, all right, if they're in this role, they're supposed to see this, but not that, vice versa. And that, that works very well. It's been around for a long time. But you were not able to say, okay, now once this person sees this row, I don't want them to see this column. It wasn't really an option. You had to do some things, maybe move it off to a different table. There were a few ways to kind of handle it, but I think truly like object level security, now you can say this column, only these roles are supposed to see this column, or maybe even this whole table. So you could take sensitive information, put it in a table and say, this is secure. So definitely something to check out if that is a feature that has, you know, been maybe missing, or for some people even preventing them from going to Power BI, that it couldn't do that. So you do have to use Tabular Editor,
Brent,
things like that.
I would even add on to that you know, object level security has actually been around already in Azure Analysis Services. And so if you're, you know, that's that kind of last nail in that coffin going from Azure Analysis Services to premium, is that hurdle there. So it was really cool.
Good. And so, yeah, exactly. If you're, you know, if we're thinking about Azure Analysis Services, really now Power BI Premium becomes like all the stuff you get in Azure Analysis Services, but more. And except with one exception, a big gap was object level security. Now that gap is pretty plugged. So they're about ready to roll on that. I'm sure Azure Analysis Services will continue to be offered for a long time. I don't think there's a retirement roadmap necessarily. I just think it's like, maybe why not do Power BI Premium at some point? Yeah, so those are some of the big announcements I wanted to cover. Then, let's see. Oh, thanks, Zoe. You're posting a new message here. Oh, nice. Oh, okay, yeah, thanks. I'll share that.
Yeah, I tried to do it in the Zoom, but I couldn't figure out how to do a file.
No, thanks. Yeah, you can't share screenshots in Zoom. That'd be crazy. That's why we need to switch to Teams, isn't it? But yeah, so this is what it looks like. Thanks to get to the trial. I guess you can upgrade or try it for free, right? So you can go ahead and pay for it if you want to, I suppose, if you feel like it. But 60 days, you get it for free. All right, I think that was it for things I wanted to cover. Since it's only been 3 weeks, we haven't had a whole lot of change in the product. Last time we talked about Power BI Premium per user. So if you have more questions about that, definitely check out the content on the user group site or on our YouTube channel where the recording is. And we'll also be posting that this meeting on YouTube as well as a follow-up. So with that, I'm probably not going to get too much in Greg's way any longer. And I'm excited to introduce him as our speaker. He sent me a couple of intros. One was the intro that he wished he had something to do with like beating Jules Verne's record, flying around the world in a balloon and something like that. But really, his true introduction is that, as I mentioned, I first met Greg in 2018, where I actually saw him speak kind of keynote at a local Power BI event. And what he really stood out to me because his presentation was funny. His professional headshot, he put his professional headshot up behind him, all clean cut. I think it's the one I had in the slideshow. And then he got up there, he's got this nice long beard, he's got the glasses on, and he's just cracking wise the whole time. So people really appreciated and enjoyed and learned from his presentations, and they had him back as a speaker several times. I do happen to know just from talking to him that the sport that he likes to follow best is judo. So there's a fun fact about Greg, and there's many fun facts about him. So he's based in Philadelphia, so often can't make it to our local meetings when we gather in person. It's a little inconvenient. And so I'm really glad that we're doing things virtually so we could have him come and speak. So with that, Greg, I'll go ahead and turn it over to you and make sure that you are allowed to share your screen if you want to and that kind of stuff.
Definitely. I'm not. You've disabled this. So thank you all for coming.
No.
That's everything I have to show, apparently.
I think you should be good now. You should be officially a co-host, so you can even just kick me off if you want to.
Yep, there we go.
Thanks.
All right, and is everyone able to see my screen?
Yes, sir.
All right. Are these videos showing up on the right in the screen share? Because that's going to get in the way.
No, I'm just seeing your slide that says an introduction to column store technology.
All right, perfect.
Yeah.
So As Brent said, my name is Greg Baldini, and I do have to caveat this up front. I do work for AWS, but everything in this presentation is representing me and my own views and is not on behalf of AWS, who is otherwise, I'm sure, a great source of knowledge on Microsoft products. So to get started with, I want to talk a little bit about me. I'm Greg, as we've covered 3 times now. I have a lot to say. I tend to move pretty quickly, and I very much want you guys to stop me and ask questions as we're going. This is definitely a small enough group that we can treat this as more of a conversation than just a presentation. So please just come off mute and start talking to me if there are any questions or anything you want to see more of or hear more about. If you like what I have to say, my contact details are in these slides. I'll be sharing the slides with Brent after this, and he's also recording this session, so you can revisit these as needed. And finally, I think just to get things started off on the right foot, this is what I look like on the internet. I was required once to get a professional headshot for work, and I have a friend who has Photoshop, so I had a lot of fun with that. With that, we're going to get into some more interesting topics. I've divided this presentation up into 4 major areas. The first is just to introduce to 2 different methods of database storage and get familiar with what we mean when we're talking about a column store. Then I'm going to dive into a lot of specifics about Vertipaq specifically, which is the column store engine that we know and love in Power BI and other Microsoft products. And then the tabular model, which is an additional layer on top of that Vertipaq engine, which is what we're really interacting with day to day in Power BI or any of the other associated products. We'll take a little bit of time to talk about query and how this interacts with the data storage and with that tabular and Vertipaq model. And then finally, we're going to talk a little bit about some modeling implications, ways that we can take this understanding of how the column store engine is implemented and use that to arrive at better models, and also answer some questions that have come up repeatedly for me when I've talked about column store with people in the past, and addressing some of those. But again, as we're going through this, feel free to stop me and ask questions. I may defer things to a later section if we've covered it, or we can just answer as and when things come up. So with that, I want to get started talking about sort of the traditional method of storing data in a database. And here we're looking at a high-level view of what data might look like on disk or in memory for a traditional database. This is row store technology. So we have some amount of metadata associated with this data table. That includes the names that you see up there at the top, and it would also include type information about the different fields that we're seeing. And that's stored sort of separately from the data that's actually representing, or the data that's actually stored in there. So the metadata is always sort of held off to the side. When we're talking about storage subsystems, this is going to be true of disk, whether that's spinning Rust, whether that's a solid state flash, or whether that's something in memory. All of these things are storage subsystems. And from the CPU's perspective, all of them are light years away. Even main memory RAM is hundreds of nanoseconds away from the CPU, and the CPU is executing more than 1 instruction per nanosecond. So all of this stuff is far away from the CPU. And so it's useful to understand how we can access that data. It's always going to be via some paging mechanism. Memory and data on disk is represented as pages. These are typically in 4 kilobyte chunks, but this is customizable and can be much larger on modern systems. And I don't want to spend too much time on hardware, at least not in this talk, but we certainly can talk about hardware implications for this data model later if that's a question anyone wants to dive into. But the key thing is that when we're reading data from any of these storage subsystems, we're getting back a page at a time. And that's really the unit of currency in reading data or writing data. We're typically dealing with these 4K or larger chunks at a time. And the way that data is laid out is that this data is often going to be larger than 4 kilobytes. So we need data that makes up a table to span multiple of these pages. And so in a traditional row store, what we have is that the first field of the first record is stored in the first position in that page. The second position is going to be the second field for that first record. And the third position is the third field for that first record, and so on. So that a contiguous chunk of storage is going to be 1 record. And if you want to read that record, if you know its location, and that's a big if, but if you know its location, you can go directly to that spot and read out that whole record in 1 read out of that page, and then have that record to operate on. The sort of follow along with this is if you want 1 field out of every single record, say I wanted to average the tenure of all of these people, well, I would have to read the whole record for Bob, and the whole record for Georgette, and the whole record for Mustafa. And then out of each of those records, I could then extract the one field I'm interested in, that tenure field, and then I can do my mathematical operations on that. And so the critical thing is that the contiguous chunks of storage are occupied by disparate data, all of those coming together to form a single record. This is how most databases are storing data on disk. The obvious alternative here, given that we have a two-dimensional data structure, instead of storing slices this way, we can store slices this way. And that's what a column store engine is. Again, we'll be operating and storing data in pages, but here, each column is separated out into its own sort of logical chunk. And the idea of a table becomes a little bit more nebulous in this representation, because we could just as easily have a fourth column there that lives in the next set of pages that could be associated with some other table. Here, if I want to do that tenure average again, what I can do is I can read the single page that points at the tenure values, and I can operate on those directly. And so instead of having to read many pages filled with data that I don't actually care about just to get to that one little subset that I do care about, here I can read pages and pages and pages of storage, however many records there are of tenure, but I'm only reading that. And so, like I said earlier, all storage subsystems are light years away from the CPU. And so the more that we can optimize the storage that we have available to us, the better. And so if I want to operate on all of the values in a single column, a column store is going to allow me to optimize my reads. So all of my reading bandwidth, whichever subsystem I'm speaking to, all of that bandwidth is dedicated to this subset of data that I care about. Of course, the follow along with this is that reconstructing a record is somewhat difficult in this column store schema, because to get a single record, well, if I want to know about Mustafa, I have to go to that first set of pages that hold the names, and I have to go to the record offset that holds Mustafa. That's the third one. So I have to grab that out. Then I have to go to a different page that's holding all the higher data information, and again, go to that same offset. And then I have to do a third operation going to that tenure page and pulling out the information associated with Mustafa's record offset in there. And so getting a whole record is relatively expensive here, but getting all of the data in a single column is very cheap. So the column store and row store are basically the yin and yang of each other. In a row store, it's very cheap to get a whole record, but very expensive if I want to operate on a single column. In a column store, it's very cheap if I want everything in one column, but very expensive if I want a whole record at a time.
So Greg, this makes me think about one of the biggest frustrations I hear people saying with Power BI is that, well, why can't I export more data? And this seems like it's relevant to that question.
Absolutely, yeah.
Yeah.
So Power BI is really, or this Vertipaq engine is optimized around aggregation. Power BI is a BI tool. And so if I want to export records, that three-step process for this sample table that I talked about, I have to do that actually per record. So I have, for these three columns, I have 3 times the amount of work to export all of the rows compared to if I were doing this in a row store. Because in a row store, I just go through, bang, 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 hit all the columns, and I get everything right out. For this column store, I have to reconstruct those records before exporting them out from the database engine. So it's relatively an expensive and memory intensive operation. So it does not fit well to the pattern here. Row stores are great if you want to dump data out, if you want to operate on a whole record at a time, or if you want to update things. Row store is really great. Doing updates and writes into a column store, especially the Vertipaq column store engine, is quite expensive in terms of computational power and in terms of RAM. Typically, you'd be copying and modifying whole pages at a time just to update a single value within that page for a column store engine. So it does get quite expensive. And that's just an important thing to keep in mind. This is a database built for a specific purpose. And one of the purposes it is not built for is large-scale exports.
You. Yeah, that's a good point. And it's one of those things that there are so many features when I hear, okay, it won't chart this thing, or I wish we had object level security, that I could come around and say, that's on the roadmap somewhere down the line. Don't let that totally decide your product selection, because down the line that feature is likely to be fixed. But as far as exporting large amounts of data, I don't see that they're ever gonna. It's just not the way to do it, right? Don't
Exactly,
jam
yeah.
data into Power BI only then to come and reconstruct it. Like, yeah.
It's a very, very fast database engine for reading, and specifically for reading subsets at a time, not for reading the whole thing at once. So that's the high level overview of the two different primary methodologies in storing data for a database. I want to get now into some more specifics about Vertipaq. So first, I just want to talk a little bit about some terminology here. Vertipaq is the name for a column store engine that Microsoft developed, and that is shared across a number of their products, including SQL Server, clustered column store indexes, as well as the various analysis services and Power BI, Power Pivot products. So Vertipaq exists in all of these. That first one actually has a very different interface to Vertipaq. You go at it via SQL queries and SQL statements. These last four are sort of all just different masks on the same thing. These all use the tabular model on top of the Vertipaq engine. But Vertipaq is actually more broad than Power BI, more broad than analysis services. And so within Vertipaq, we've got a few different ways that we can actually store and encode that data. And I want to talk a little bit more about Vertipaq before layering in the stuff that makes up the tabular model or Power BI. So first, we're just going to focus in on some implementation details of how column store can be implemented. One of the benefits that we hear a lot about Vertipaq and about Power BI is that there's great compression in the engine. And this compression is really stellar, but it's not the normal kind of compression. We're going to look at how it encodes data to understand what that compression looks like. So the first thing is actually not a compression scheme. It is just value encoding. And in this, we have various values of data. Here, I've just excerpted out that tenure field in our sample table that we were looking at. And here in a value encoded column, what you would see is that every value that exists, it just represents itself. So numbers in Vertipaq are 64-bit integers. Each of those entries in this column are 64-bit integers. This is typically where you'll see the best performance for fields that are being aggregated, because there's no additional overhead in getting this value out. If I'm compressing that data, there is some small overhead in decompressing or decoding the value that I need to operate on. So there's no overhead. You're just accessing raw values. The bits and bytes that exist in RAM represent the values directly. And so this is typically going to yield slightly higher performance for fields being aggregated. And it's also going to yield the best performance both in terms of query and in terms of storage efficiency for very, very high cardinality fields. And so when I say high cardinality, what I mean is the number of unique records that exist in a column as a proportion of the number of total records that exist in that column. And so high cardinality is really, it's a percentage. It's what percentage of a column is unique. And so the highest possible cardinality is a key field that is all unique values. There's no repetition. Everything is unique. And that is not going to compress too well. And so trying to compress it can actually lead to worse memory efficiency in storage, but it can also lead to more overhead in actually querying and reading those values out. So we'll get a little bit more into how you can use this knowledge later, but this is one thing to keep in mind. Fact fields that are being aggregated often will benefit from a value encoding. The next encoding methodology in Vertipaq is run length encoding. And this is one of the things that can lead to huge compression ratios in Power BI and in the Vertipaq engine. Here, instead of storing the values of data, we'll store a value. And if that value then repeats in the next contiguous record, we'll just say how many times that it repeats. And so here, instead of having one row and then the next row, and then the next row, and then the next row, what you might actually have is a value and then an offset that says, here's the first time I see something different after that. And so we can see on the left-hand side here, this value encoded idea of this tenure field. And I've just added a few more rows here. And on the left, we're repeating the number 1 3 times, and we're repeating the number 4 4 times. And on the right-hand side, what we can see is we can actually store that as, well, the first record at offset 0 has a value of 16. The second record at offset 1 has a value of 28. Then records 2 through 4 all share the same value, that being 1. Records 5 through 8 all share the same value, that value being 4. So for anything that is sorted, this is especially common for dates in a fact table. If data is coming in sorted by the date, so you just see a string of 1,000 of January 27th, 2021, well, those 1,000 instances of that value can be replaced by a single small record that says, here's the date, and here's how many times that thing shows up before the value changes again. So this is one of the things that can lead to huge compression ratios, especially with low cardinality or highly repetitive data, depending on the sort order. And when loading or refreshing data into Power BI or Tabular, the engine is actually doing a lot of optimization work here, testing out various sort orders to determine if there's a better sort order for your data to get a better compression ratio. In general, you're not going to beat it. If you try to sort your data going in, you're going to do a worse job than the heuristics in the engine will determine is the optimal sort order, because you need to understand what is going to lead to the longest runs when sorting by potentially a dozen different columns. And so you need long runs of repeated values, and preferably those repeated values should be very, very big. So if you had a string that's 100 characters long, repeated 20 times in a row, that's going to lead to much better savings than an integer that's repeated even 50 or 60 times in a row. So you need to account for a lot of very deep knowledge about the data, and computers are much better at looking at lots of small bits of data and coming up with a conclusion based on them than we humans tend to be. The third type of encoding that we see in Vertipaq is dictionary encoding. And this is sort of for lack of a better term, this is the default in Vertipaq. Most of your fields will end up dictionary encoded in Vertipaq. And what this does is it says, I know that there are repeats within this field, but they might not all be contiguous. And so what we can do is we can represent values with a minimally sized bit string to represent it, to be a key to look up to that. So if we look again at this same sample column, we have 4 distinct values in that column. The values are 16, 28, 1, and 4. Each of those values is a 64-bit integer, but since there are only 4 distinct ones, we don't need 64 bits to represent a unique value here. We only need 4 bits because we've got 4 options. And so that 16 we can tie to a key of a 2-bit string of 00, 28 to 01, the number 1 to 10, and the number 4 to 11. And what Vertipaq will do is actually choose an optimally sized key based on the number of unique values that exist in your field. So if I had one more unique value, I'd actually need 3 bits. And so there is some overhead because 3 bits can represent 8 values. So even if I have 5, there's some small overhead there, but much smaller than storing these values directly, because the smallest thing that you can represent in the Vertipaq engine in terms of the data types is a Boolean. A Boolean is actually not much, is just a bit. I apologize. So a Boolean is not going to see a lot of compression here, but anything besides a Boolean is at least 64 bits large. Strings have some overhead, and individual characters are 8 bytes plus the overhead. It's going to be 8 bits, plus the overhead, it's going to be fairly large. Any number is going to be a 64-bit integer or a 64-bit float, or it's a fixed decimal, which is actually also a 64-bit integer under the hood. Date times are 64-bit floating point numbers under the hood. Everything that you're storing is at least 64 bits, and longer strings might be much more than 64 bits. So you can see a lot of benefit in this dictionary encoding. And so this typically sees the best compression for columns that have relatively low cardinality, medium to low, but that are very large columns. So there are a lot of repetitions in there. Even if those repetitions aren't directly succeeding one another, you'll still see this compression benefit. And so just as a little bit of a summary here, we've got those encodings. Encodings can actually be mixed as well. So something can be dictionary encoded, and we might say that in this field, we've got something that has the key of the bit string 0012, or sorry, 0010. And so that's a bit string, but then we could say that bit string repeats 20 times in a row. So these can actually be mixed together. And we can use Tabular Editor to set an encoding hint if we know for a fact that something should be encoded in a certain way. Typically, I'll only use this for setting up fact fields that are going to be aggregated to set those to value encoding. So because I know that value encoding is typically going to lead to better aggregation performance. We can also understand what the data structures and what the encodings are by looking at a model in Dax Studio. So I'll actually pull that up here. And as I'm pulling these up, I just want to note that these two tools, Tabular Editor and Dax Studio, are absolutely critical as you're getting more advanced in Power BI or in Tabular. They're definitely things that should be in your tool belt. I don't want to derail this into an introduction to the tools, but I just want to make sure that these are on your radar. And if you're serious about Power BI, you should also be serious about adding these two tools to your repertoire. So first I'll pull up just a very, very simple Power BI model here. This is one of the first ones in my save history, and the data that's in here does not actually matter. But I just want to show we've got a single table in here. There are a few fields in this, and Tabular Editor is just another way to look at this exact same model. It doesn't give us anything to do with the visuals in the model, but we can deal with the tables and all of the various metadata about these tables. So in Tabular Editor, what I can do is I can actually open from a database. And it knows how to identify the local Power BI instance that's running and connect directly to the model there. It gives a little bit of a warning because some of the features are experimental, and I turn all of those on immediately and then click right through the warning. But it is something to keep in mind. If you're going to be using Tabular Editor on Power BI files specifically, save your Power BI file, have a backup. You can corrupt it. In general, Tabular Editor in its defaults is not going to do anything destructive to your model. But if you're like me and you just click OK to everything, you can actually affect your model. So here on the left-hand side, we've got a tree-based view that you can expand out these different nodes. And these represent the objects that exist in your model. And what I want to look at specifically here, there's a lot of functionality in Tabular Editor, and I'm ignoring almost all of it. What I've done is I've expanded out this table, and I've selected a column. And then what I can do is I can scroll down over here. And what we can see is all of the metadata about this column. And one of the options, one of the settings that you can set for a given column is an encoding hint. And this tells Tabular Editor that I really, really think that this column should be encoded in a specific way. You can't force it. The engine can override you, but in general, it will do its best to follow your hint. And you'll note that run length encoding is not an option to choose here. I can choose hash, which is the name for dictionary encoding internally to the tabular model, and value, which is value encoding. Run length encoding can always be applied, and so it will be applied opportunistically if it can be, but we can choose whether we want to tell the engine that it should use a hash encoding using a dictionary and a lookup, or if we want this value encoded. And I'll typically go through and value encode all of my fact fields that can be aggregated. And within Tabular Editor, you can actually script this to be able to say, go look at every table that has fact in the name, and any field that is numeric, set that to a value encoding. So you can automate a lot of these sorts of activities in Tabular Editor. But again, this is not a Tabular Editor presentation. So I just wanted to point out that we can set these hints here. Then the other tool that is useful is to understand the current state of a model is Dax Studio. And so Dax Studio is another companion tool. And what we can do here is we've got a query editor, so you can write arbitrary DAX expressions. You can evaluate those queries and run them and get to a lot of useful information about the query plan. We'll look at the query plan a little bit later. But the critical thing I want to look at right here is, again, when you open up Dax Studio, it can automatically detect the Power BI instance running locally. So you have to have Power BI open, and then you can connect to that model. And what you can do is you can navigate to this advanced tab and select View Metrics. And when you select View Metrics, this is going to give you a breakdown of the data size, the storage utilization, and some other metadata about every single column that exists in this model. And it can break it down into tables as well as columns. This is super useful if you're looking at trying to optimize the space used by your model. If you've got something that's just consuming a lot of space and it's bigger than you think it is, you can come in here and look for your worst offenders and use that as a starting point for troubleshooting space issues. But another thing that it has is an encoding field here. This is going to say for every single field that has been loaded, what is that encoding that's been chosen, whether that's value or hash encoded. And again, run length encoding can be opportunistically applied to any encoding, to any other encoding. So you're not going to see that as a specific value here, but know that if you have strings of repeated values, those will be run length encoded within here. So I know I've
Greg,
covered.
is it possible
Go
to
ahead,
see,
yeah.
can you get a sense from those numbers, like here, the compression percentage, although I'm sure that's, a naive way of looking at these numbers, but like, how much space did that particular encoding strategy save? Or I don't know, it's probably hard to tell. You could probably just compare the cardinality to the column size and see.
So there's no direct measure of compression efficiency. What I would probably do if you want to break this down is you could go to your data source and look at size there. So any database engine will give you similar space consumption reports and metrics. Excuse me. And so you can find that out from a database source. If you're looking at something like a flat file, well, everything in a flat file is going to be Unicode characters. And for the most part, Unicode characters are 8 bits. And so you can just assume that you can calculate that size pretty directly. Numbers in text files are represented as text. So the number 1 is 8 bits and the number 10 is 16 bits, despite the fact that in Vertipaq, they're both a 64-bit integer. So there is some stuff that you'd have to do there, but you could calculate this. It would be a bit manual and a bit annoying to do so, but you could also script a lot of that out. You could also probably use Power Query and Power BI to do a lot of that calculation if you wanted to, but you'd have to you would have to do that work. There's no like built-in report for the compression efficiency that
Makes
you see.
sense. But you might just, this certainly could give you a sense of where to attack first if you're having model bloat or model size problems that you
Oh,
might
absolutely, yeah.
think about how
So
you, yeah.
the default sort order when you pull this up is column size. So you'll see your worst offenders at the top. And there's a little bit to keep in mind. The first thing is that column size is going to be bigger than the raw data. And the reason for this is that the tabular engine has a lot of metadata that it maintains. Some of this is for compatibility with the legacy multidimensional engine in analysis services. Some of this is its own bookkeeping. So data is actually the raw data size. Dictionary is going to be the size of the dictionary if something is hash encoded, but this is also maintained as a data structure, even on value encoded fields. So there is 120 kilobytes of data that is actually dedicated to each of these columns, even when they're value encoded. And then this hierarchy size is entirely multidimensional compatibility. So hierarchy size does nothing for you in Power BI, does nothing for you when you're querying with Dax, but it does everything for you when you're in Excel. So if you're analyzing in Excel, hierarchy size is basically presenting a multidimensional compatible view of the metadata of this model, so that Excel, whose pivot tables only know how to speak MDX and the multidimensional protocol, Excel pivot tables can interact with this data seamlessly. You can also query an analysis services tabular model in MDX. I mean, that's what Excel is doing after all. So the compatibility is nice, but for the most part, if you're coming from the Power BI world, all of this is just overhead. So unfortunate, but it's there. But as soon as you use Analyze in Excel, it is no longer overhead. So use it once and you've paid for yourself.
Gotcha. Okay, thank you.
And I do want to just take a quick stop here because I know I've thrown a lot of fairly dry stuff at you and not lived up to Brent's promise of humor in presentations. But I do want to just take a quick stop and any clarifications or any questions I can answer based on some of what we've looked at so far in terms of storage technology. All right. Well, if any questions come up, please feel free to stop me and I'm happy to answer those. So the next bit, now that we understand some of the building blocks, is understanding how whole tables actually get built in Vertipaq. So we've got two critical things that we want to keep in mind, segments and partitions. And the shortest summary I can give you is that segments are internal bookkeeping and are also the unit of currency for parallelism in the engine. Partitions are the unit of currency for administration and operation. So partitions are things that you define, segments are things that the Vertipaq engine will create on its own. Partitions are objects within a table that have their own unique query. You typically will use these for incremental or partial refresh of data in a table. And partitions are going to sort of dominate segments in a certain way. A segment cannot span multiple partitions. And this is a problem if you define many, many partitions such that the size of data in your partitions is much smaller than the segment size would be otherwise. So within Power BI, the default segment size is 1 million rows. Within Analysis Services Tabular, the default segment size is 8 million rows. And basically, all of this compression that you're seeing, each segment has its own dictionary. Each segment is going to be a thing that can be scanned independently. It's a thing that can be refreshed independently or otherwise processed independently and in parallel by the Vertipaq engine. Partitions are things, like I said, that you define. So if you define a whole bunch of partitions, say a partition per day, and you see maybe 50,000 rows of data per day, well, you've given up most of the compression benefit and most of the parallelization benefit by making that segment too small. So you want your segments as large as they can be. Within Power BI, it's not customizable. So you want your partitions, your incremental refresh to have sizes of at least 1 million records, preferably larger. And in Analysis Services Tabular, you can tune your segment size. For very, very large models, larger segment sizes will often actually yield both compression and performance benefits. But really, that should not be the first thing you reach for. You should be doing much more basic tuning before you get into segment size modifications. But segments are the things that are actually being compressed. So the more data is in a segment, the better compression ratio, because the dictionary is at that segment level. So if I have 5 values in a segment, I'm not going to get much benefit from that dictionary. But if I have 8 million rows and 1,000 unique values in that segment, I'm going to see great compression benefits because my dictionary values are much smaller than the raw values there. So this is an important thing to keep in mind, but most of what we'll actually worry about in terms of Vertipaq implementation, in terms of optimization, is really based around segments. Partitions are really more of an administrative feature for us, the humans, who need to deal with processes that are represented in our data. So this is, given what we know, this is what a table in Vertipaq actually looks like. This is a single column table. And what we see is that there's the table. There's some metadata associated with that table, namely which columns exist, what the types of those columns is. Then you'll have a column. There will be a column level dictionary, which holds all unique values that exist in that column. Then there will be multiple segments that make up a partition of that column. There will always be at least one partition. If you don't create any, you'll just have one single partition that represents all data in the table. And then that will have segments within it for each column. Each of those segments has its own dictionary, and those dictionaries are unique from one another. So you'll see in each of these, I've shown that segment 2 only has 2 unique values, and so it only needs a single bit to represent its keys. And so this is all of these views are a little bit of simplification, but all of these are directionally correct and will give you the proper intuition when considering this. The fewer unique values in a segment, the better compression and the smaller your dictionary will be. Whether or not it's exactly 1 bit representing that is an implementation detail that I am not privy to, and Microsoft doesn't seem to be willing to share all their source code with me. But the direction here is absolutely correct. And so you've got a table. There could be multiple columns. Each column would look like this within that table. I have here the partition existing within the column, and that's a little bit of a lie because the partition both exists within the column and without the column. Partitions are a table level construct. You define them for the table, but then each column is an individual unit of storage and so has partitions within it and segments within that. So it's impossible to draw a box that is simultaneously inside and outside the column box. So I've done what I could here. But this is ultimately, in terms of data structures, what a Vertipaq table would look like. And you might have another column that has no dictionary encoding. If it's value encoded, there would be no segment dictionaries there, but there would still be a column level dictionary. When you're using the values function in Dax, you're actually reading the dictionary directly. So that is why values is often a very, very quick thing to do. Getting distinct values is often a slow operation in most data processing systems. But because of the way this data is represented, calling values is reading out of the dictionary. And so getting distinct values in Dax is among the most efficient implementations of distinct that it is possible to achieve. And so that's one of the benefits in terms of analytical queries, because distinct counting is perhaps not the most common thing we do, but always very useful. And it is optimized very well in the Vertipaq engine. So I've tried to be very careful to separate using the Vertipaq engine and the tabular model, because these are in fact 2 different concepts. Like I mentioned earlier, the Vertipaq engine is also shared into SQL Server, and the tabular model is a construct sort of on top of that Vertipaq engine. And so Vertipaq is fairly primitive. It understands tables, it stores tables and columns, and it has a few data types that it can store in those. And it can basically do basic arithmetic. It understands how to represent relationships between those tables. And you can do simple sort of filter predicates, basically literal values. So, X is greater than 5, or this string is equal to that string. Those sorts of literal filter predicates, but not much more complex than that. But what it can do is it can do all of these things in parallel. And all of these things are going to be operations at the segment level. So if you have 20 segments in a column and you're operating on that column and you have 16 cores in your laptop, well, it can operate on 16 of those at a time. So that's the unit of parallelism that we're seeing. And you might think, I said earlier, you actually sometimes want to increase your segment size and decrease your segment count for very, very large data tables. And you might be thinking, but Greg, more parallel equals more good. So shouldn't I want to make my segments as small as possible, and then I can be super, super parallel? And the reason for that is not the case is sort of twofold. One is that you only have so many cores in your machine. And when I say very large data models, I mean data models where the number of segments is multiple times the number of cores that exist in your machine. So that's the scale for large in this case. And the second thing is that parallelism is good, but has overheads. And if you try to operate on individual data elements, individual numbers separately per core, the overhead of parallelism is absolutely going to dwarf any benefits that you see. And so in general, you don't want parallel processes that are a significant multiple of the number of cores that you have. And so if you have 10,000 segments and 8 cores in your machine, you're actually going to be paying some penalty for the coordination overhead of parallelism, but you're not getting the parallelism benefit because you're only operating on 8 things at a time. So in general, you want something that is relatively small integer multiple of parallel tasks of the number of cores. And that's a hard thing to tune in Power BI because you can't change your segment size, but that's why many small segments is not a good idea, and relatively fewer large segments is a good idea. If your segment count is similar to your core count, you're fine. If it's a couple times, you're also fine. If it's thousands of times, you're in trouble. And then the formula engine is basically the rest of Tabular, all layered on top of the storage engine that is primarily Vertipaq. The formula engine is advanced functionality, and that is unfortunately also single-threaded. So any functions that you hear of as iterators all utilize the formula engine and will be will operate serially on all of the data, despite the fact that it might exist in multiple different segments. So in general, the pattern that you want to follow is to have your sort of things that can be parallelized. So basic arithmetic, your filtering expressions, that sort of stuff should be inner. That the innermost functions are going to be executed first in Dax. So the innermost things should be the most basic operations you can be, and the more complex things should be operating on the results of those inner operations, because the complex things will be single-threaded and therefore slower in the formula engine. And again, this is not going to be a deep dive into query plan analysis, but I do just want to show how we can use Dax Studio to understand some of the server timings and the query plan that happens in a query. So I'm just going to do a very simple query here. I'm just going to do evaluate on my data table, which is going to return all of the values that exist in this. And it's a very small model, so this is not going to be too big of a problem. And in Dax Studio, we can see the history of queries that we've run. We can see the results of those queries. But having turned on those server timings, I can actually see what the breakdown of the query engine, whether it's the storage engine or the formula engine, that's happening here. You can see a breakdown of what operations the Vertipaq engine is actually doing. And you'll actually see something that looks a little bit like SQL over here on the right-hand side of these server timings. This is sort of a representation of what will be sent to Vertipaq. This is not code that can be executed, and you could never write something like this and have it be executed. But this is a representation of the queries that will be sent to Vertipaq to be executed. And if you look at the query plan, this is actually physical operations in the Vertipaq engine. If we look at this first thing that's happening, spool iterator, that's actually that is a class that exists in the C++ code of the Vertipaq engine. And that is the class that is being instantiated to be able to evaluate this query. And then within that, we've got several operations that are happening. And there's also metadata that's being captured, how many records the engine estimates it's going to be operating on. So there's a lot of detail in here. And again, this is not going to be a deep dive on Vertipaq query internals, but Dax Studio is the way to get into this level of detail. And if you've got queries that are not performing or measures that are not performing the way that you expect, these are absolutely critical tools. First of all, the server timings to understand where time is being spent in operating on this, and then the query plan to understand sort of what operations are happening in here. There are some really good posts by the Italians, as all the really good posts are, about using the Dax Studio for for investigating query plans in Tabular, and I would definitely recommend giving those a read. If you just search for Dax Studio or query plans on the Italian site, sqlbi.com, you'll definitely find some good stuff that goes into a lot more detail here. But the critical thing that I wanted to point out is just that we can understand where our time is being spent in these two. And you might think this is kind of slow for a query that's just getting the data back out. But toward Brent's question from way back at the beginning of the talk, this is giving you all of the data that exists in the table. This is dumping all of that data out. This is essentially what would happen if you were running an export process. And so we see a lot of time in that's actually stitching these results back together. And that's where a lot of this formula engine is coming from. Reading the columns out of the storage engine, super fast, 26 milliseconds here. But stitching all of those things together into result sets and into records that can be presented back to the client, in this case, Dax Studio, the client tool, that is where all of our time is being spent. But if I wanted to aggregate this, it would be a lot quicker because we would just be focusing on that storage engine query for the basic arithmetic. So those are the two components that make up the tabular query engine. And then all of the various metadata that you operate on in terms of setting relationships, setting those data types, that is happening in the tabular modeling layer. And some of that data is pushed down to Vertipaq, like the data types and relationships. But all of the formatting strings, the actual existence of measures, any DAX code, that is actually tabular constructs. Some of that is translated into and sent to Vertipaq constructs for query. But all of the stuff that we operate on or interact with, that's all tabular.
Greg, before you moved on from that, without going into too much detail, like you said, but in Power BI, I just wanted to mention the view, they call it Performance Analyzer. In Power BI, under the View ribbon, there's something called, I think you have to be on the, yeah, there you go. There's something called Performance Analyzer. It's just the second from the right. Yeah, there you go. And so if you want to know how to get the DAX query, you hit start recording, you refresh your visuals on your page, and then you can just like copy the query. Yeah, so if you expand quantity, so it's showing you each visual as each visual runs a query. And I don't know why that one's blanked out, but you could usually click copy query. Maybe you have to hit stop first, Greg. Maybe that's
Yeah,
what
I
it
think
is. Okay, I don't know why that one didn't let you copy the query, but yeah, I guess you can click refresh too. There you go. Now you can copy it, and then paste that into Dax Studio. So yeah, at least just a quick. Here's how you can do like a quick 3-step process, and at least get a sense of. I mean, you could at least look at those two numbers, the yellow and blue, and say how much formula engine, how much storage engine. Obviously, it did this one very fast, so no problem there. Yeah.
Yep, yeah, absolutely a good call out. And one thing that I'll mention is that the exact workflow that Brent just described and that you saw me doing, that is basically the only good part about the performance analyzer is extracting the query from a specific visual. The reason for that is that this level of data, first of all, the DAX query is sometimes very wrong in this performance analyzer. Oftentimes it's right or close to right, but it can be very, very wrong and misleading. Visual display doesn't really tell us anything we can do anything about, and other also doesn't tell us anything we can do about. The only lever we have to pull on for optimizing is changing the DAX, and the only lever there, we can't change the DAX of a visual. We can change the DAX of our measures. And so the most useful thing that you can do is copy the query out, come over to Dax Studio, and then operate here and get real timings, for lack of a better term, from Dax Studio's server timings and query plan, and do all of your optimization here. And then once you've got a measure that's performing better in that sample query, you can take that measure back to Power BI. But the timings in Performance Analyzer are unfortunately not very useful for optimization. It is useful for at least showing you which visuals are the slow ones, but the slow visuals are almost definitely slow because of the measures in them. So that's my hot take on the performance analyzer. But that workflow is super useful. And when I've done lots of optimization work in Tabular, I do follow that exact workflow, except as soon as I'm out of Power BI, I'm in Dax Studio and doing hours in Dax Studio and then 5 minutes in Power BI to get the query back out again. All right, so we've touched on queries a little bit. So Dax is the query language, and Dax is purely a tabular model construct. Like I showed earlier, Vertipaq it's got its own query internals, and we never touch those or really interact with them, except by poking from a very, very long distance by writing DAX code. Our DAX code eventually gets turned into storage engine queries and into Vertipaq code to get the data back out, but we can only influence that Vertipaq sort of opaquely by changing our DAX, and the way in which DAX is optimized and translated into storage engine queries is not something that we've got deep insight into or something that we've got much control over. So the other big thing that I want to call out for queries, and where we can start to see some of the benefits of the Vertipaq engine and how it can make the types of analytical queries we're doing so quick, one of them is segment elimination, which is somewhat similar to partition elimination in a traditional database engine, but a little bit different. This actually examines the dictionary of a column segment, and if the value that we want or that we're filtering on does not exist in that dictionary, we can skip the rest of processing of that segment. If the value does exist in the dictionary, then we can process that segment however we need to for the operations at hand. But what this gives us is a very quick way to weed out or to rule out large swaths of data that we don't need to do any more operation on. So we can very quickly narrow down to the subset that needs work done on it, and then do that work on that subset of data. So this is one of the critical things that comes out of Vertipaq and how it makes things very quick. The other is that the storage engine caches very aggressively. So this combined with segment elimination is actually very powerful because it's caching things at the segment level. And so if we've got two similar queries that have maybe the same filter, but they're evaluating different measures, something like that, or if we're clicking around and if we're clicking in Power BI and we change a filter, but we're sharing most of the other existing filters, like we select a different date, but we keep our product filter and we keep our customer filter, well, the caching will still benefit us there because this caching is going to be happening at the segment level. And if a given customer did not appear, it's likely that it's not appearing again. And so we actually get that caching benefit at the segment level. And so I don't think I'm doing a great job of describing this, but basically we get benefits even when the queries are changing from the caching because of the way that our DAX query is decomposed into multiple different storage engine queries. Those different storage engine queries can each be cached at the segment level. And if we change our DAX query in such a way that it shares many of the storage engine subqueries, those subqueries are cached, even if we are introducing one or two new non-cached storage plan queries or storage engine queries. So this is everything that I wanted to cover on sort of the internals and how the Vertipaq engine is implemented in and affects DAX and the tabular model. And I want to take that and then turn it a little bit more concrete and practical with some modeling exercises and some modeling guidance based on this understanding that we have to get better performance and or better compression. Often the two go hand in hand out of our models. So I'll stop here though, because I've covered, I know, a lot of technical stuff, and we're going to get into something a little bit more concrete, but also leaving some of those technical underpinnings behind. So any questions or clarifications I can give at this point?
I really liked the way you're explaining this, Greg, because one of the things, with clients, they say we have all this data and they're like, but it's really hard to kind of guess like how it's going to play when we put it into Power BI. They're like, oh, it's, taking up all this space in the database. But I'm like, well, it's very different when you take it from the database to Power BI. The compression is different, so a lot of times, I explain, very simply that, if you have a million, 2 million rows, 8 million, 10 million rows of just integers, and it's like, there's 3 values, you're going to have a very small model. You give me 8 million rows of text that's this long and it's unique every single row, that thing is going to be massive.
Yeah.
So trying to explain that compression and how that works, and then also on the refresh, how everything dumps in and then increases that memory load and then comes back down once it's done its thing, is it's always an interesting conversation to have. Typically, if we work with really large sets of data, it's like, well, can we be fine in Pro? Do we need to go to Premium? How big is this data set going to be? Kind of thing. So, but yeah, it's really interesting how to see kind of, all those things, and especially about the segmentation as well. And when you're watching like the incremental refresh on partitions, you'll see it has those kind of, it always goes and makes those partitions in the history kind of bigger after it uses them. So it'll have like a month, quarter, year, and it'll keep that thing. And, now that makes sense as to why it would do that.
Yep.
But yeah,
it's I think, the first step in getting familiar with Power BI or with Tabular, the first thing is getting comfortable with the model and with DAX, which is a big hurdle on its own. But then after that, you can get really far with just building some intuition around DAX and not understanding these underpinnings, but then you'll hit another really big wall. And you hit it hard usually because you scale to a certain level. And no matter how good your intuition on DAX is, if you don't have a good feel for what's happening in the storage layer, you're just going to keep bouncing off of that wall and either by luck bounce over it or just stop and say, this is how far Power BI scales, or this is how far Tabular scales. And I'm lucky in the consulting I've done to have gotten to work on models that are hundreds of gigabytes large after compression, tens of billions of rows of fact data in multiple fact tables. And I recognize that's a scale that most companies just don't have data that exists at that scale. So I've gotten to, or had to, been lucky enough or unlucky enough to have dug into all of these internals and done so with a couple of peers of mine. And so once you start to build this intuition about the storage level and the storage layer, you can write code that is going to absolutely fly compared to stuff that you used to think was pretty good. So it's a big hurdle, and it's not necessarily required for every model. If you're in single-digit millions of rows, you probably don't need to understand any of this, and you're going to be perfectly happy. But when you start getting into tens of millions, or especially hundreds of millions, understanding the storage underpinnings really does help. And having an intuition of how the model works under the hood, as it were, really does help for optimization. All right, so I'll move on to the modeling exercise. And this is one of my favorites that I've actually worked on. It's a challenge that comes up fairly often, and it's twofold. One part of it is just how can we frame a problem so that we can understand it effectively in terms of a dimensional model. And this one also has a great aspect of how does this fit into the compression and the performance characteristics we understand about the Vertipaq engine, and how that's very different from what people would see in a more traditional database environment. And so here what we've got is a business problem, a challenge, pretty much exactly as it was presented to me. And so I've kept it in some unclarity, and I'll clarify as we move through this. But it was presented in a somewhat muddled way. The most important part is actually the second to last bullet, but the person who was asking for help with this did not understand. But their business requirement is a month-to-month headcount. They want to be able to slice by a whole bunch of different things. And the way their data was represented in their source database was essentially as a bunch of different event tables, and they thought they could model these as slowly changing dimensions. The reason that they thought that is that there is a pretty good pattern in the Kimball books about events in progress. And it's got lots of great examples, and it's talked about with slowly changing dimensions, and it sort of looks like it fits onto this exactly. And it sort of does fit exactly, except it's a bear to implement because every single one of these things they want to slice on is a large chunk of code that is almost identical to, but not quite identical to, the rest of the code they've already written. And so that is, in other words, exactly the sort of thing that we humans are terrible at. Big things that are the same with very small differences, and you have to get those small differences exactly right. And any change implies rewriting something that looks nearly identical. So this is how we eventually boiled it down after some conversation. They want to be able to count headcount of employees over time. They want to slice by the employee name and other attributes of that employee that might exist in an employee dimension. They also want to know in any given time period how many new hires happened in that time period, how many rehires happened in that time period, and how many promotions happened in that time period. And they also expected that the number of things they might want to slice by, the number of events they might want to account for, would increase over time, but they didn't have specific examples there. And so this is how you might represent some of those events. And this is not far off from what their data looked like in the database, obviously cleaned up and simplified a lot, but it roughly looked like this. It was denormalized a little bit more, but we essentially had this stream of things that had happened. And this is an example scenario where the employee is hired on the 1st of January, and they were hired in as role number 1. They did such a good job that in a week and a half, they got promoted to role number 2. Role number 2 was not a good fit, so they left after 5 more days. But then, we loved them so much that on the 20th, we came back and offered them a big raise and come in as role number 3, because that's really where you belong. And so these are the things that happened. And obviously, in the real world, these would be spread out a little bit more. But this represents the types of data and the types of things that we'll need to be able to track. And what I would want to do is stop here, and I'm not going to force audience participation if you don't want to, but feel free to speak up if anyone does want to. But I want you to just think about what are some of the things that we've talked about in terms of how data is structured that we might be able to take advantage of. And a couple of leading questions are, what are some of the relationships that we would want to build or that we can build with this data? And the other leading question is, what things are true at what times, and how does that interact with the relationships? So if anyone does want to participate, more than welcome to, but again, I'm not going to force audience participation. But I do just want to give a little bit of time to sort of think about these, how you might approach it. And it's not a test, but sort of how can we reframe this in a way that's going to have properties that fit in well with the storage technology we've talked about.
I mean, I'll start us off here. Each of those
Go
things
for it.
looks like a dimension, possibly employees, relating to a dimension, dates always, and the event. So like, can you rather, you certainly like storing events as text like this will be bad, really bad, and hard to analyze.
Yeah, and
They
we've
should
got
be
freedom to transform this
okay.
in any way we want to.
Yeah,
So this
they
is
should.
just the shortest way I can summarize it.
So they should be abstractable to some sort of type: hires, promotions, and quitting. You have at least that. You have at least those three kinds of events. But as far as then, what's kind of embedded in here is the roles, exactly to what role. But I'm not sure they did want to slice by the role dimension too. So
Yeah, how many role ones do we
hmm.
have in January? How many people got promoted to role 2 in January? How many people got promoted in general in January? So I'll call out one thing, and this is one of the first hurdles that we run into. You're absolutely right. Each of these we could clean up that event thing to be more structured, and we could build relationships from each of these. Employee key going to an employee dimension, that's not going to be a problem. We want to slice on employee attributes. Date, though, gets us into some trouble. We can absolutely build a date dimension. That's easy. Hopefully we'll have a date dimension in our back pocket already. But then we build the relationship. So on the 1st of January, we hired someone. Okay, that, if we want to count hires in January, we could slice to January and we could see that hire. That seems fairly reasonable as long as we clean up the event a little bit. But then do we say how many people are working for us in February?
Yeah, so
So
for
go
this
ahead.
one, you would probably just do a disconnect the date table. That's how I would usually approach
Yep,
this.
we can absolutely do that. And that leads immediately to the second hurdle, which is that these things are essentially durations. And so we need to, if we want to select a date, we need to understand the date that's selected, and then we need to find everything in here that's less than that date and everything in here that's greater than that date, and find where that date is actually in a period that we care about. So specifically, we don't care about the 15th to the 20th here. And those are two events that bookend something. That's a duration, but that's a duration where this person was not a part of our company. So they did not contribute to headcount, and they did not contribute to any hire or fire events that happened between the 15th and the 20th. So it's a duration, it's a bookended thing that we would likely capture in any logic that we want to use with that disconnected date table. But it's a bookended thing that we now need to figure out why we don't care about it. And for each bookended event that we might identify, we have to figure out, do we care about it? In what way do we care about it? What event does this represent? So it's absolutely doable, and it's not a bad approach, but it gets into more code than I like to write.
So the design pattern that I think of from Kimball would be in this case would be a factless fact table, right? Where we would have possibly an event type that we could say that we would be able to slice on to say here's a termination event, right? But I'm not sure how that design pattern plays into the structures that we've talked about here already.
Yeah, so that's a really good thought. And again, it's got a challenge. The challenge on that one is simply, it's more of an ETL challenge, but how do we distinguish this event on the 20th from the event on the 1st? Because we cared about rehires. So how do we identify a rehire? And it's more of an ETL question, but it's still something that we need to address. And so there are definitely challenges here. And I'm not intending to tell people that they're wrong. This is something I got wrong twice when working with this person before getting to the model that I now consider to be the correct answer to this and similar challenges.
One other naive way I've seen people do it is just a snapshot. So every day, who was there? But you still have the same rehire question, right? So you could take the snapshot on January 1st, and Mr. 1 was there, and on the 20th, Mr. 1 was there. But how do you know they were rehired? But that's one way. People kind of exploded into more granularity. Every day, who was there, what role were they in, and then on any given day, if that's as granular as they want to get, you can draw that picture.
So what are some of the challenges with an approach like that, exploding it out?
Well, data size. You're basically generating data unnecessarily.
What kind of data are we generating?
I don't know.
A snapshot of hire, fire, and promotion events. Yeah.
Table might look something like that.
I've done the snapshot approach as well.
And so, well, what do we know about long strings of repeated employee key number 1?
It would be compressed, yeah. Run length.
How would employee key get compressed here?
Run length.
Definitely run length. Also, probably a good opportunity for a dictionary. How about the role key? I mean, this is a weird example where this person changes roles 3 times in 20 days. But
Mhm.
realistically, how long is an individual likely to remain in a role?
Yeah, several days. Yeah, many
Probably
days in a
hundreds
row.
or maybe thousands.
Hmm.
Dates, okay, well, those are not run lengthable here, but do the dates repeat across employees? So that's going to dictionary encode pretty well. New hire, rehire, all these different flags. These are going to be a whole bunch of zeros repeated, and then every once in a while a 1. So this thing compresses like crazy. And it is, you described it as the naive approach, Brent, but this is what I honestly do consider this to be the way to approach this class of problems. Because what we can do is
Yeah.
we can
I'm
write it
sorry.
in just, oh,
I
go
was
ahead.
probably thinking of that in like row stores. You know what I mean? I've seen
Mhm.
people do this on the row store level.
Oh yeah,
And
and
then I thought
it's a
maybe
dog.
that.
It's
Yeah.
an absolute dog in a row
Right.
store.
Yeah. Yeah. Interesting.
And so this is why I like it. It's an interesting framing problem. There are multiple approaches you can take. None of them is inherently wrong. They all have different challenges. This one puts almost all of the challenges onto Vertipaq engine, which we didn't write and we got for free. So that's one challenge addressed. And it puts the other challenge on ETL time, which is it's a legitimate challenge. We still have to get this logic out of however that data is represented. We do need to identify when a hire event is not the first hire event for a person, and encode that as a flag here. So there's still work to do. There's no magic. There's no silver bullet. But in terms of how this works with the Vertipaq engine, this thing flies. So we talked about distinct counting being pretty much as efficient as a distinct count can be in the Vertipaq engine. The only measure you need here is a distinct count of that employee key. If you select a month at a time, well, distinct count on an employee key collapses those multiple records. If you want everyone who's hired, well, the distinct count of employee key with new hire flag equals 1. That's everyone who got hired. You can easily combine that with your date dimension slicers. So the reason I said earlier I don't like writing that much code is because for this problem, I know that this is how little code I can write in Dax. I can write distinct count employee key and be basically done with my Dax. And I like Dax, it's a fun language, but it's also the hardest to debug, the hardest to performance tune, and the least well-known of all of the tools I could bring to bear for ETL. And so if I want to be able to work with other people who don't like Dax as much as I do because their brain has not been warped by using it since 2013, if I don't have a bunch of those people around, then I can lean on other technologies to do the ETL side of things. And then I can load this into Power BI. Or into Tabular. And so this thing compresses like crazy. I've built this for a lot of customers. Even without compression, almost all of the data in here is literally 1 bit per row. After run length encoding, this is like thousandths of a bit per row of actual storage that we need to keep this. So this does eventually hit a scaling wall. One customer I was not able to implement this for had customers, and their customers numbered in the 10 million range, and they had 20 some odd years of history. They had a number of different attributes they wanted to track about those customers over time. And you can do that math. It's a big number, and eventually compression, I mean, it doesn't fail, but even compressed giant data is still kind of giant. So for that customer, we just did this by month, and then we were happy because they didn't actually need the date grain. So it's always worth poking and prodding there, but I really like this one because it does force us to sort of reimagine our intuitions about what is naive or what is a good fit for a storage engine. Specifically because this is exactly what Vertipaq will chew up and spit out very happily and very quickly, but it will also bring most other database engines to their knees. Or if not to their knees, at least not perform in any good way. So I also want to take this a little bit more abstract and some general themes that have come out in data modeling work that I've done in Tabular and in Power BI. So one thing that I am consistently surprising myself with, even after having come across it, is the amount to which you can solve problems by making your tables taller. It's really incredible. There are things that I've looked at and thought that's not really going to be doable, or I'm going to have to write a lot of code. And then I figured out how I can represent this variability as a flag or as a label. And then I can just make my table 10 times taller, but 10 times taller isn't a big deal for Vertipaq with these labels. And repeating that data with different labels or subsets of that data with different labels, I can then take this thing that was a hairy code challenge and turn it into a pretty simple modeling challenge. Again, this might be pushing complexity to ETL, but I will always take that bargain. I will always happily pay ETL time to make query time and report time simpler and faster. I'm always going to take that deal. So repeats are great. If you can take some idea of a concept of a thing that we know, where we can look at a table and then know something, if we can represent that knowledge in just more rows in a table, we should absolutely do that thing. Materializing knowledge is one of the pithiest ways and least helpful ways I know of to describe what good modeling is. But if we can materialize our knowledge into tables and into columns and into relationships, we're going to be in good shape. Relationships are the next big thing. So we didn't get into relationships too much in the implementation, but one thing to keep in mind is that relationships in Power BI, in the tabular model, in Vertipaq, relationships are physical objects that exist. They consume RAM. Relationships exist in memory. This is an object that represents essentially what exists on two sides. And it's oversimplified. It's basically a bitmap saying this thing exists on side left and side right. And if it exists on both of those sides, then the relationship exists. So relationships are similar to, but are very different from joins in SQL or any other language. And specifically, a relationship will perform much better in tabular than the function natural inner join or natural left join. All of those join functions in Dax will perform significantly and measurably worse than a relationship that has been built into the model, because these are physical entities in the model. That's hugely powerful. And so if we can lean on relationships, and even if that means making our tables 10 times taller to be able to represent this thing as a relationship rather than as code, that will often be a performance win and not much of a storage space cost. So the next thing is, oh, go ahead.
I'm gonna say, Greg, so I really like this that you have this. I have to run off for just a minute there where you're talking, but the taller versus wider, you know, I see this a lot where they'll have say like a net or gross column.
Mm-hmm.
And so they'll have those two columns, and I'm like, well, first thing I do is I just stack it and then just have a net or gross flag, just because it makes my life easier. But I found that it will, even just having even though they put them in different tables, like we'll have the same data, they'll have a net and a gross table, you know, I'll tend to stack it because it tends to bring the model size down and it's more performant. I think that's, you know, kind of playing to your first guidance there.
Absolutely, yeah. That's a really good example with like two different tables that mostly share structure. Well, if they mostly share a structure, they're probably also mostly sharing keys. And since we need column level and segment level overhead, well, segment level overhead doesn't change if it's two tables or one table, but column level and table level overhead is absolutely reduced by taking these things that repeat and putting them in one place. And so it's, again, it's an intuition in, you know, traditional database. It's 6 of one, half dozen of the other at best, because you're going to pay the same storage cost in either of them. But in tabular, because first of all, the relationship is a physical thing, and because we've got repeated values now, that actually makes our performance improve. It's unintuitive if you use any database besides this one, and it's incredible when you use this database. So the next thing that sometimes will really come out as a gotcha for people, I've got two specific instances, but the idea is just how can we reduce cardinality in a column? Can we make a column have fewer distinct values? Because that's going to give us a couple of benefits. One is a big one on dictionary size, but the other big one is the smaller a dictionary size is, also the smaller our dictionary keys are. And the smaller our dictionary keys are, the more keys we can see in a given amount of time. We're ultimately limited in bandwidth of RAM when we're dealing in queries in tabular. So if we can see more things in the same amount of RAM space, then we will see more things in less time in a query in tabular. And so if we can find ways to reduce cardinality, I don't care if we're adding rows to the table. I don't care if we're adding, for this one specifically, if we're adding necessarily width to the table. I just care if we're reducing cardinality in columns, and we'll see huge benefits. So this is a really fun example that you can test out on any model of your own. If you've got dates and times in a fact table, try building that table with a single date time field, and then take a look at how much space that takes up in Dax Studio, looking at those statistics. Then take that date time field and just break it out into a date field and a separate time field. And the time just has 86,400 rows if you're at a second grain, fewer if you're going to minutes or hours. But if you break that apart, you'll be shocked at how much space you save by taking the same data and representing it as 2 low cardinality columns instead of 1 very high cardinality column. Date times are never a substitute for a primary key, but in practice are often nearly unique. The nearly is the thing that gets you in trouble if you try to use it as a primary key, but nearly unique is almost as good as unique for trashing memory consumption in the Vertipaq engine. So it's a fun experiment to try. Another one that often catches people out is that we might have floats that exist in a source system. And if we're looking at a traditional database, if I have 64 bits allocated to a field for a float, well, I'm going to use all 64 bits because floating points are represented in 64 bits or 32 bits, whatever fixed size. But if I've got a float that has 15 decimal points of precision, and I'm doing math where I round this off to the nearest integer, I probably don't need all 15 of those decimal places. But if you take a decimal out to 15 places, that is, again, nearly unique. And it's for data that we actually don't care about. So if you can truncate these things down to a lower precision of decimal places, you can actually see big wins in memory consumption of a given column. So again, this is very situational. You might need all of those decimal precision places, and that's fine. But if you don't, it's worth asking the question. Oftentimes, if you pull up your table statistics and your column statistics in Dax Studio, you're going to find that your date times and your floating points, and sometimes your fixed decimals, those are going to be the things that take up the absolute most space because they just have the ability to be so much more unique. If you truncate things off where you can, you get a lot of benefits. And so those are 2 specific examples that are fairly common. But in general, if you can find a way to reduce cardinality, you'll see benefits. And then finally, the last thing is dimensionalize. So dimensional models work very, very well with the Vertipaq engine. And I hope by now you understand more than just because someone with authority said so, but actually why a dimensional model makes a lot of sense for this. But this is something that can go a little bit too far. So I want to take one counterexample here, and I'll break that down. So all of this within reason. So the question that comes up is, why do I not just take one huge table? If everything's stored as a column, it doesn't actually matter which table that column lives in. And I just talked about this, and I said it as a positive thing, but relationships take space. So if I have all one table, I avoid the relationship overhead. I'm not paying any extra on column overhead. So why is this not a good thing? And this is, this will probably tell you as much about me as about the problem, but I have had a dark night of the data soul struggling with this question and why a single table is not a good modeling approach. Like I've actually lost sleep over this. Hopefully you haven't, but if you have, I hope I can help a bit. But this is a big question, and especially with a database technology and a storage engine like Vertipaq, there are a lot of things that point toward a single big table. It will work very well. It'll have good performance, and it might have better performance than some simple dimensional models, specifically by avoiding relationships. But it's not a good general approach. It might be a good specific approach, but here's 3 reasons why it's not a good general approach and why it shouldn't be your starting point, although I'm perfectly happy for it to be the end result of optimization where you've tested and validated that it's the right fit for you. So the first problem of using a big fact table as a general approach, well, eventually you're going to bring in another fact table. And maybe these things don't share granularity. So I still want to filter across these. So they share some granularity. Date exists in all of these tables. Employee key exists in 2 of them. Product exists in all of them. Customer exists in only 1. Now, if these are one big fact table, I have to answer a lot of questions really fast, and I have to get them exactly right. How do I distribute budget to inventory? And it's hard to get a nonsense question right, but that's a question you have to get right if you put all these in one table. But you might think I can just keep everything in there and just use a little bridge table between 2 or 3 really, really big fact tables. Well, I want you to find a way to relate all of these in a way that does not get Power BI yelling at you for what's the specific error? It's too many paths or circular dependency in relationships. Relate these together using just a little bridge table without getting a circular dependency error. And you can't do it. You can't do 2 tables together with 2 bridges, actually, because you need bidirectional tables to relate 2 facts together via a bridge. And as soon as you've got those bidirectional relationships, if you try to do two sets of those between two tables, doesn't matter how many bridges you get there. This is an intractable problem. Now, if you never need to see these things alongside each other, if you never want to build a matrix visualization that has sales quantity and inventory quantity both next to each other for a given date, that's fine. As long as you don't need to see this data alongside one another or filter it by the same dimensions, you're good. You can keep them separate. But as soon as you want to have multiple fact tables, logical fact tables in there, you're going to need to eventually have multiple physical fact tables, because allocating budget to inventory does not make sense, but you would have to do it to put both of those in one table. And building relationships among these three is impossible. And I welcome you to build an appropriate bridge table that actually solves this problem. But as soon as we've got multiple facts, we need dimensions that exist on the one side of one-to-many relationships to each of those facts. I cannot keep attributes in the fact tables. So that's why I can't have a single large table. So that's one of the things. But maybe I don't have multiple facts, or maybe I can reasonably distribute things among those. So the next thing is what I just categorize as reasonability. This is a model is something that helps us to reason about data. It's not just a way to represent bits and bytes to the computer, but it's also a way to represent business processes to humans. And so to represent things to a reasonable human, a human will be able to reason about the thing. That's, to me, what the core of reasonability is. Can I reason about this thing and come to valid conclusions given what I know about it? Well, if I want to dump everything into a big table, all of a sudden I'm going to have 4 names at least in that big table. Well, I can't have 4 fields with the name, so I need to subdivide those in some way. So I'll have customer name, I'll have employee name, I'll have manager name, and I'll have product name. Okay, well, there might be descriptions for multiple of those. There might be phone numbers for multiple of those entities. So then I'd have customer phone number, employee phone number, manager phone number, and maybe I have, a half dozen or a dozen attributes. It's not unreasonable for a dimension, a logical dimension, to have a dozen attributes that describe a single physical thing. And so as soon as I've got that, I need to build a taxonomy in my fact table by prefixing everything as customer something, employee something. And as soon as I've done that, I've created dimensions just in a fact table and made them harder to use. But I need to be able to subdivide against these things that might otherwise share names. So it's a bit of a naming problem, and it also makes it very difficult to find the things that you need unless you know the naming convention because you built it. The last one is being able to work with the language. So Dax is, as I mentioned a couple times, our only way to actually get at Vertipaq. So even if a whole bunch of columns represent the data reasonably enough in a single table, with Dax, we can't operate on that in a good way. So common thing is to remove all filters from a single dimension. If I've got a single big fact table, it's got all of those attributes just dumped in there like a sack. Well, if I want to clear all filtering on product, I have to individually name all of those product attributes that exist in that big fact table and not name any of the non-product attributes. And as soon as I add any product attribute to that table, maybe I get a new description, or maybe I get a color that I want to add in there. As soon as I add product color to that big fact table, that first expression is incorrect because it does not remove all filtering on products, because it does not account for color, because color is, in this scenario, new. So I cannot have maintainable correct code and data that has any rate of change. So the second expression, if I have a proper dimension, that all dim product is always correct, no matter how many attributes I add to dim product. It could be 1,000 column wide table. That's its own problem, but it's always correct in that that expression is removing all filtering on the product dimension. And it's just impossible to maintain something like that in a big fact table without changing your code every time your data might change. And that is not a situation you want to be in. So those are my 3 primary arguments against the single giant table. From a technology perspective, Vertipaq doesn't care, but we're not operating solely on Vertipaq, and we're not able to write Vertipaq expressions. We write Dax, we're building models for humans, and ultimately we want to be able to interact with more complex models. So a single table might work for some specialized scenarios, but it's not a good general approach for these couple of reasons. So that's everything that I had that I wanted to cover. And I just wanted to open it up for any questions or discussion, anything. I love this stuff. I hope that comes across. And I'm happy to stick around for questions, answer anything that I can.
Well, I think that your love for it definitely comes across, and we greatly appreciate it, Greg. This is this has been a big learning experience, I know, for all of us. And so I'm really glad I recorded it, because I'm going to come back watch it again to remember the things that you talked about. Really, really appreciate you putting this together for us. And I know some of our group may have some stops it's about 1 o'clock Central Time now. And so for those that do, I want to make sure you can get away for that. But just want to say, Greg, thank you very much. And yeah, if anything comes up later, or if you want to get in contact with Greg, like he said, his contact info is in these slides. So we'll post it on the user group site, and eventually we'll have a new community page where we post it. And then, yeah, we'll put this on YouTube, and I'll let you guys know on Twitter and on LinkedIn, at least, when that's all done. But yeah.
Greg, I'm going to be very interested to talk to you a little bit more about slowly changing dimensions in Power BI. That's something that I pretty much resigned myself to not being able to do that. And so, you know, it's something that I think about, you know, Power Query is a great way to model transaction level detail and that type of thing. But that, you know, I would really, I truly would need to, you know, utilize a more traditional database technology in order to handle slowly changing dimensions. So that's something that I found that really interesting that you gave that some treatment.
Yeah, I pulled this back up to the slide with my contact details. Like Brent said, this will all be shared. Feel free to reach out. But you're touching on a really interesting topic there. So I've called this a database a few times, and we absolutely should frame Power BI as a database technology. But it's a very purpose-built database technology.
Mm-hmm.
And like I was mentioning at the beginning, writing isn't easy in Vertipaq in general. Within Power BI, writing is basically impossible outside of the bounds of a refresh. So if you need to maintain state, like in a slowly changing dimension, to say this record has now changed in a way, and here's the the validity values for that. So here's a new end date, and here's a new record that almost looks like the old one, except it's got a couple changed attributes and a new date on it. That sort of thing is not something that you can actually maintain in Power BI. I'll backtrack. You could do it with incremental refreshes, and it would be awful. But I could come up with a way to build it into an incremental refresh that no one would ever want to work with. So it could be technically feasible with incremental refreshes, but it's not reasonable in any way, shape, or form, and not a good idea. So practically impossible, although technically could be done. But yeah, you definitely need some other store of state, some other store of data to be able to implement slowly changing dimensions properly.
Yeah. Okay. That was actually kind of my understanding is, you know, I thought if I had to, I could probably get to it with an incremental refresh, but
I mean, I put that in there just because I don't want to lie. But like, don't do it. Don't tell. Just don't. No, it would actually be awful.
Yeah.
It's not something you want to do. You would to do it correctly. I'm pretty sure you would have to have Power Query querying its own model during refresh to read the state out of that table that holds that state, and then use that to derive what I need for the new state, which I think should be possible in an incrementally refreshed Power BI model. But again, don't do it. Like, I stared into the abyss and the abyss stared back. That's the territory you're moving into.
All right. Thank you, Greg.
Yeah.
Greg, this is Thomas. I have a question. So typically, when I'm building models, let me get this on the right screen so I'm not looking in the sky. When I'm building models, I'm really thinking about developing a model that when it lands in Power BI, my DAX is going to be as simple as possible.
That's the way to do it.
And I know the answer to many of these questions is it depends, but at what point did you find yourself when you're getting to performance tuning where you had to generally go back and think about, does this model need to change to work with Vertipaq better?
So it depends, but not in the way that you meant it. So part of it is I am lucky enough to have been using this technology since 2013, which relatively few people can say because it was in development as of like 2012. I'm very lucky, and I am now at a point where I'm going to design my models in the first place that in a way that they respect the Vertipaq strengths and weaknesses. So it's, for me, I'm likely not to come to a model redesign as an optimization in my first few rounds of troubleshooting, but that's only because I've already done that for years and gotten to the point where I'm usually not shooting myself in the foot with the model. So that's why it's a sort of it depends answer. In general, the model is a great place to look for optimization. I'd say the lowest hanging fruit is looking for iterators on the inside of your function calls instead of on the outside. That's going to be the lowest hanging fruit, and that's a broad class. But if you can, and there's no good reference for this, unfortunately, but once you have a feel for which DAX functions are formula engine versus which DAX functions are storage engine, basically any of your basic arithmetic, basic math is going to be storage engine. Once you get into financial functions, those are likely to hit formula engine. Anything that's an iterator, any of the X functions, add columns, filter, those are all formula engine. Anything that's complex should be on the outer edges of your function calls. Your innermost function calls should be doing filtering with raw predicates, not using the filter function, and should be doing like arithmetic and table operations. So if your innermost stuff is table operations and your outermost stuff is iterators and more complex functions, that's the best pattern of DAX. And that's usually where I'll look first to make sure that I've got known formula engine triggers on the outside so that they trigger on the already processed data that's hopefully as small as possible based on the storage engine operations that have happened inside. So that's really broad, but that's where I'm usually starting when I'm looking at troubleshooting performance. And then when I get into, like if I really need to bring something down by, more than 50%, that's where I'll look at model optimizations. But usually big wins are achievable in DAX because DAX is such an opaque language. But if you've started with a good dimensional model, it's almost definite that you'll get your quicker wins in DAX. But the model's always worth considering, but I wouldn't start there.
Thank you.
Sorry, that turned into a little bit of a ramble. I don't know if that helped.
Absolutely. Thank you.
It's good. Get to know which ones are storage engine, which ones are formula engine so you can think about that as you're writing your DAX. Yeah, it's great. Well,
One
go ahead,
really big thing. Any of your, especially your iterator functions that take a table, never pass them a raw table because like we talked about, constructing a table takes work. So if you pass in a reference to, my table name, it has to construct records for every iteration for every step of its iteration. But if you pass in a single column by using values and just the column name, or if you pass in just a couple columns by using like group by on the table and just extracting out a couple of columns and not taking all of the columns, that's a huge win often in performance, and something that I see people get bit by because, again, tables do not exist. Bags of columns exist, but if you want your bags of columns to look like a table, you have to do work. So if you can operate on columns instead of tables, you are doing less work because, again, tables are bags of columns that need to be constructed. So that's another big one in optimization.
So follow-up question on that. So, rather than passing a table, passing a column, then what if I have to, walk through a couple different relationships and from that column? I mean,
So you can lean on, if you need to navigate the relationship so that you have a single logical table that has columns from multiple physical tables, you can use group by on whatever table is the base of those relationships. So whatever is pointed to, it's on the many sides. So if you group by and your first argument to that is your fact table, you can reference columns from all of your dimension tables that are related to it. So you can pull in columns from multiple different tables, and that will navigate the relationship just fine. If you have something where it's where they're not sharing a relationship, you need to figure out how to construct that table. Sometimes cross join is the fastest. Sometimes it's faster to just slap the two things in a cross join and let the iteration go over the whole thing than doing more complex logic to make a slightly smaller table. So depending how dense things are, depending how much of the cross join actually exists in the data. If all of the cross join actually exists in the data, then it's fastest just to cross join it, because that doesn't need to do any logic. It just slaps the two things together in a Cartesian product. If it's relatively sparse, where the Cartesian product is much larger than the amount of stuff that exists in fact, then it may be worthwhile to do something with more complex logic to just get that smaller subset. But don't be afraid of a Cartesian join if it is close to reality.
Well, thank you very much, Greg, for your time today, and thanks everybody for being here and the great questions. I know Greg can really be a font of knowledge on this topic, and so glad that you all were here to take advantage of it. And yeah, so please join us again on May 20th, 4 or 5 weeks. And Greg, thank you very much, sir.
Yeah, absolutely. Thanks
All
all.
right.
Great
Yep.
fun.
Yeah. All right. Have a good rest of the day.
All right.
See you
Thanks,
later.
everyone.
Bye.